Welcome to the first lesson on impulse and momentum. Until now, you know that an object in motion has some properties. It has inertia, according to Newton's first law, meaning that an object resists a change in motion that depends on its mass. An object also has kinetic energy while it is in motion. The motion itself can be described in various measurements of displacement, velocity, and acceleration. But how does one measure the amount of movement of an object? The answer is that we measure a combination of its mass and velocity. Momentum can be described as mass in motion. It's found by multiplying the object's mass in kilograms by its velocity in meters per second. So the combined unit is kilogram meters per second. Now, direction is very important for momentum, unlike kinetic energy. Kinetic energy is a scalar, while momentum is definitely a vector. That is the most important thing about momentum. So, objects that have a velocity and a mass have momentum. Now, something of great importance is how objects get momentum. To make something move, according to Newton, you must apply a net or resultant force to the mass. The object will accelerate and begin to increase in velocity. How much velocity is added to the object depends on how long the object is pushed by the force. So, now we have a relationship between the force, time, mass, and velocity. Now, the mathematics in the derivation isn't something you are likely to see in an exam. But the concept of force acting on a mass for a period of time is important. That is the definition of something called impulse. Impulse has no symbol of its own and is simply the force acting for the change in time. But, very importantly, it is equal to the change in momentum of the object. So, by combining the equations of momentum and Newton's second law, we get a new way of looking at Newton's second law of motion, and this is important to know. Newton's second law in terms of impulse can be stated as such. The net force acting on an object is equal to the rate of change of momentum. So, that's saying that the force we must apply to an object is determined by how much momentum must change and how long the force is applied. This has a great effect on how much force an object experiences during a collision. When an object changes direction in a short amount of time, it has the effect of increasing the force applied to the object. When airbags deploy, the effect is that the collision of the driver's head begins much earlier and lasts much longer. The initial and final velocity of their head is the same. We can say that the impulse of both of these collisions is the same, but the time of the impact on the left is much longer. Thus, the force of the impact is less, saving the life of the driver. Because impulse uses vectors of force and velocity in its calculation, it's important to keep note of the signs and directions during an example. When the ball in the picture bounces on the wall, it initially collides with a velocity of 40 meters per second and rebounds, or bounces away from the wall at 20 meters per second. If it has a mass of 100 grams, what is the magnitude and direction of the impulse of the ball? As with any vector question, start with indicating a positive direction on your diagram. In this case, towards the wall is chosen. You can choose otherwise and still arrive at the same answer. Next, let's list the information we were given. The initial velocity meters per second as it is towards the wall, but the final velocity is -20 because it is away from the wall. The 100-gram mass of the ball must be used as kilograms in physics, and now we are ready to calculate. So, substituting the values for the final and initial values for velocity, make sure to use brackets for the negative sign. The answer itself works out to be an impulse of -34 kilogram meters per second as a magnitude. But all vectors should be written in final answer as a positive number with a direction. Since the answer is negative, that means that the impulse or change in momentum is 34 kilogram meters per second away from the wall.